Lecture 15, Distributed Loads of Engineering Physics 2P04. So a distributed load is a load that's not placed at just one point like the loads we've been dealing with before. Now we're going to be dealing with loads that are distributed along a surface. So we're going to usually use the symbol W. W is the force per unit length. So to find the force, you just integrate W with respect to x. And to find the moment produced by a little bit of that w dx, you would just multiply that w dx by the displacement. So the total torque would be the integral of that over the entire surface. Let's explore this with several examples. In this case here, we've got a constant distributed load. We've got a linearly increasing distributed load that goes from 0 at B to 6 kilonewton per meter at C. And we've got a linearly decreasing distributed load as we go left to right anyway, from 4.8 kilonewton per meter at A to 0 at B. And we're asked to set up the equations, not necessarily solve, but set up the equations to determine the reactions at the supports for the beam and the loading shown. Okay, so you can't really tell that much from the diagram. Maybe you can, but this is a pin support, this is a roller support, so we've got B, X, and Y, but just C, Y. Force equation in the X direction tells us that Bx is 0. In the Y direction, we've got by plus cy, and then the contribution of the distributed load, right? So minus the integral of w dx. W is telling us the force per unit length, so we just integrate that with respect to the length over the whole beam to find out the total force in the y direction. Now the integral of w is the area under that, right? So there's 3 different sections. We probably will have an easier time if we split it up into this first section, the second section, and this section, and calculate their areas separately. So the area of this triangle is just the height, which in this case has a different unit than the base. So we've got 4.8 kilonewton per meter times the base, 0.9, and then divided by 2. So half of the base times the height for a triangle. Same thing for the other one, and then the rectangle is just the base, 0.6 meters, times the height, 6 kilonewtons per meter for the total force of that. Okay, and that's the equation you would need to find the, well, actually that's 2 of the equations that you would need to set up. You can't actually find the force, the reaction at B or C from that. We need the torque equation to close things out. The torque equation is a little bit more complicated just because we've got to figure out what W's function actually is. So we can't use the area trick like we did for the force equation, for the torque equation. For the torque equation, we've actually got to write the function. So we're going to have an easy time if we find the torque about B, because this is a 0 point for these lines. So you know how the equation of a line is y equals mx plus b? If you pick an origin so that the line goes through that origin, then the y-intercept is 0, and you can just get rid of the b. It's just y equals mx. Conveniently, by picking that as our 0 point, also the torque formula just becomes the integral of x times w dx. Okay, so let's find out what some of these w's are. For this one, w is easy. It's a constant. It's 6 kilonewton per meter. So the torque about B is going to in part contain the force from this distributed load. If we say that counterclockwise is positive, then we'll say minus 6 kilonewton per meter times the integral, let's say minus the integral of x times w dx, where w is now 6 kilonewton per meter. And we're going to integrate that from 1.8 to 2.4. And that's where this term comes from in the torque equation. What about cy? That's the easiest one. We've got 1.8 away, and it's just cy pointing up. So that's the familiar one we've got for calculating torques from before. The other 2 are a little bit more complicated because writing their line equations is a bit trickier. So let's do this one first. This is a bit easier. The slope is 6, and the distance, or rather the slope is 6 divided by the distance, so rise over run, so 6 kilonewton per meter divided by 1.8. Okay, so that's this right there. Rise over run, and then multiply that by x, and there's our w. So this part on the right here is w, but we've got another x because we're finding the torque produced by that w. We could have used this formula, integrated from 0 to 1.8, to find the force produced by it, and if you like, you can double check that this integral with only one x there, with just this x, not that one, will produce the same force as we got from our triangle area. To find the torque, though, we need to add that x back in. Now, the most complicated one, because of all the negatives flying around, is the first one. So here, the slope is negative 4.8 kilonewton per meter, divided by 0.9. And that's the W there. Then we've got to integrate it from x is negative 0.9 to 0. And this one is on the opposite side of things. So from our sign convention for torque, it produces a positive torque. So we're going to add that. But the distance away is actually negative x. So it kind of cancels out the positive we put in front. And if we had just ignored it and subtracted like the rest of them, it's self-consistent, which is kind of nice that those negatives cancel out. So the answer is, if you're a little bit diligent about signs and consider just some of those effects, you may not get all the negatives. So, but if you're totally diligent, then you'll get all of them. If you're really lazy, you may miss 2 negatives and it'll work out well for you. In that case, you are a very lucky person. Now the good news is, once you've gone and written out these functions in W, you can check your work pretty easily in Maple for the entire thing. So writing the functions out in terms of W, getting these piecewise functions written as functions of x is the hardest part. Then you can just use the equations that become quite easy after that. So in this case, here's how you write the function that we just came up with in Maple using the piecewise function. Piecewise is a little bit strange. Normally when you write something out, you'd say that, okay, well, x is the function of x is negative 4.8x over 0.9 as long as x is less than 0, and then it's 6.6 over 1.8 as long as x is less than 1.8, but Maple forces you to write it kind of backwards. So first you give the condition, and then you give the function. Then you give the next condition, and then the function, and then you give the next condition, and then the function. And in addition to that, you can't really give like the compound conditions. If you try and say 0 is less than x is less than 1.8 like you would write in math, Maple doesn't like that. So it kind of goes through in order, and it picks the first condition. It says, is x less than 0? If not, then let's go on to the next one. Is x less than 1.8? If not, then it goes on to the next one. So even though anytime x is less than 1.8, or anytime x is less than 0, it's also less than 1.8, we don't have to worry about it accidentally choosing this function when we wanted this function on the first part of the range. You can check that it worked by plotting it. That's always a good test to see that you've written what you think you've written. Anyway, our force balance equation is just by plus cy minus the integral of w over the whole beam. And then our torque balance equation is 1.8 cy minus the integral of x times w over the whole beam. Wow, that's easy. So it kind of all makes sense now, and it's easy. We've kind of fixed this. If you were to take an entire course in statics, so if you take Engineer 2P04, then you'll probably find that a lot of the effort goes into doing these integrals and getting kind of lost in the math involved in it. And it's hard to, when you're doing that, it's hard to step back and look at the big picture. And so this is one situation where I think it really gives us an advantage here by being able to use Maple, that we can just have a simple equation like this, and we can say, well, ultimately it's just an integral, and that's the big picture of what's going on. All right, next problem set. This is going to be an even more complicated thing we can write the distributed load functions for. So now we have a different set of supports. So just one support now, fixed support here at A. And the other thing that's kind of complicated about this compared to what we're usually dealing with is that the distributed loads are parabolas. They're not the same parabola. So this is a different parabola on the left than it is on the right. Okay, so how do you write? First of all, what are the reactions at this fixed support? It's got an x force, which is going to turn out to be 0 because there's nothing else going on in x, a y force, and a moment. So the moment, let's say, is a counterclockwise moment, ma. Let's set the y force as up and the x force to the right, but that's going to be 0. Then we're going to set x equals 0 as the left end just to write some stuff out. So last time we used a creative 0 and set it at 0 right there to make the line functions a bit easier. This time, let's not even do that. Let's say x equals 0 at the left end and then deal with writing the functions however we can. So what we'll do is we'll say this left parabola, well, we know it's a parabola, and we know that it has a 0 at 4. So that means it's got to have the equation a times x minus 4 all squared. All right? Then what else do we know about it? Well, when x equals 0, it has a height of 2. So let's substitute that in. W1 at 0 is 2 kilonewtons per meter. And that lets us solve for what a is by substituting in the 0 over here. Sure enough, we find an a, and that's it. That's our W1. Then for the right parabola, we'll do the same thing. Except now, the point that we know about it is that it's got a height of 1 at x equals 6 meters. So that lets us solve for what b is. So then our entire piecewise function is given like this. And as before, we say the net force in x is 0, net force in y is 0, and the net torque about a is 0. See if you can substitute all of this into Maple. Well, if you don't have the commands memorized, that's okay, as long as you have them written down in a way where you can find them easily on a test. I mean, if you accidentally memorize them or you have some kind of idea what they are, even if you don't remember exactly the syntax, as long as you can look it up quickly, then that's probably fine. So here I used a slightly different approach to last time. Last time I defined a function, w maps x to this piecewise function. You don't have to do it that way. Instead of that, you can just say w equals this, and now w is just going to directly get replaced with this piecewise function. That's okay too. That also works. Then we don't have to say w at x, we just say w. And I also did the solve a little bit differently. I didn't define equations first, I just said solve this thing. It's understood that that equals 0, and this one, and there we go. We can evaluate it as a floating point to find decimal numbers for this. Moving right along here, an equivalent point load to a distributed load. So if you take 2P04, they don't spend a lot of time writing the functions and then actually integrating them like we're going to do most of the time. They use another approach which works out well, and it's a useful heuristic to know. So I'll give you the tips on this too. So here's what you'll do sometimes as a check of the answer. So another way to do this is you can replace this with an equivalent single point load. So for this one, it turns out that it produces the exact same force and torque as its total force if you were to place it just as a point force in the middle, like this. How is that 600 newtons? Well, it's 6 meters of 100 newton per meter, so 600 newtons total. This one, on the top here, we've got 3 meters of 200 newtons per meter, so that's 300 newtons. And it turns out that the triangle shape is equivalent to one that's 2/3 of the way across. And there's another rule for a parabola, and you can look that up in a table and some in a mechanics textbook if you're really interested in it. But instead of doing that and like trying to get you to memorize all of the rules, what I'll do is I'll explain where these come from, how you can prove that these are equivalent in terms of generating the same force and torque. So let's look at the top one here. Why is this equivalent to a single force that's 300 newtons placed 2/3 of the way? Well, it's equivalent force. It produces the same force as if you were to integrate along it, so that has to be 300 newtons. That part you're probably not debating. But what about the torque? Why does it have to be placed 2/3 of the way? Well, what torque does it make about some point x0? So let's not even talk about the torque it makes about the point x equals 0 here at the end. Let's say some point x0, wherever that is. The torque that it makes about that is this. Now you can do that integral, and you'll find that the torque it makes is Fy, this 300 newtons per meter, what we found up here, times the difference between our arbitrary point x0 and 2/3 of the 3 meter distance. Well, wait a minute. That's the exact same torque that the force Fy placed at 2/3 of the way of the 3 meter distance would make about our point x0. Okay, so there it is. This distributed load, in terms of the net force and torque that it creates about any point x0, is the same as a single point load placed 2/3 of the way along this top beam. The 2/3 is because it's a triangle. Now you can also try and derive that for the vertical one here, using the same math as before, but the integral is a little bit easier. The net force from the distributed load ends up being 600 newtons, and torque about some arbitrary point y0 up this is the integral of the force per unit length, distributed load, dy, times y minus y naught, so our distance in the torque, the displacement. And we come up with the exact same torque you'd get for a single 600 Newton load placed 3 meters up, about this point y naught. Now at this point I want to stop and point something out here. So we found that the distributed load is equivalent to this point load in that it produces the same, it has the same net force, and it also produces the same net torque about any point on this beam. Well, what that means is the choice of point is arbitrary, and notice that we just found that this distributed load is equivalent to that exact one force that's at a specific point. What that means that if you're not trying to prove that there's such a thing as an equivalent force, but you're just trying to find out where that equivalent force should be, you don't have to use an arbitrary point anymore. You can just pick any one given point and then say, okay, well, where should that location be? Well, it should be, we should put the total force at a spot where it makes the same torque as this distributed load. And that's what we'll do later on. So how do we, before we get back to that, let's solve this problem again by first replacing each distributed load with an equivalent load. Let's see if you can give that a shot. So it's going to be this total force, but placed 2/3 of the way this way, so at 0.6 this way, and then this one at 1.2 this way, and this one at 0.3 between these ones. There you go. Okay, now follow-up question. Is it possible, do you think, to replace all three of these loads with a single equivalent load that produces the same force and torque about every point? And this kind of relates back to this discussion here. So can you do that? Well, it should be able to. You should be able to do that. So here's how you might be able to do it. You just say, well, they'll produce the same force as the total force of them. It has to. And they'll produce the same torque as a single force. If we were to place it, if we were to find the torque produced by these three about A, and then take the torque produced by a single force about A, we just have to, then we just have one variable x equivalent, which would be the location of that, and we can just solve for what that would be. So why should this work? Why do we think this should work? Well, replacing 3 point forces shouldn't be any different than replacing like an infinite number of point forces with an equivalent one. Let's just use the same logic, and that's what we're doing here. So we'll say that together they have a net force of this. That's definitely true. And where should we put that equivalent net force of 11.16 so that it produces the same torque as these ones individually? Well, we'll just set the torques equal. So we'll say that the Fyxe produces the same torque as the sum of Fy's times xi for each of these, Fyi, xi. So that is, we'll say that this variable distance spot, xe, times Fy, let's imagine it's somewhere in the middle there, times this x, must have the same torque as this one times its distance plus the next one times its total distance plus the next one times its total distance. So what it works out to is actually just a geometric average of the location of the forces. So in conclusion, then, a combination of forces is equivalent to a single force given by the total value forces located at their weighted average position. And again, these are great equivalents to use as long as you just want to solve for the external reaction forces. As soon as you want to go and look inside the object and look at what's going on internally, then you can't really use these equivalents, and we've got to go back to the distributed load calculations that we were doing at the start of this section. That's going to be necessary for the next lectures that we're doing.